If you work in infrastructure or industrial manufacturing, you already know the painful truth. Corrosion isn't just some minor inconvenience, right? It is a massive, multi-billion-dollar liability. So, welcome to today's explainer. We are diving into the hidden, microscopic world of anti-rust coatings. We're going to trace this incredible leap from the highly effective, but let's face it, incredibly toxic legacy chemicals of the past, straight through to the brilliant, sustainable, smart molecules that are driving today's green chemistry revolution. It's a fascinating space, so let's unpack the science that's literally protecting our modern world.
Okay, let's dive right into this because honestly, this concept completely flipped how I view the whole problem. Most of us picture rust as, just metals slowly rotting away, like it's just degrading. But it's actually far more active than that. Fundamentally, it's a spontaneous electrochemical cycle. Essentially, the metal's surface forms countless microscopic batteries that just relentlessly eat away at the substrate. It's wild to think about. But once we realize rust is basically just a microscopic battery, well, we can figure out exactly how to unplug it.
So for a lively metal like steel to actually corrode, it needs four very specific things to happen all at once. You need an anode where the metal loses electrons, a cathode where oxygen picks them up, a tiny film of moisture to act as an electrolyte, and the metal itself providing a conductive pathway for those electrons to flow. But here is the brilliant part. These four elements, they are entirely codependent. If you knock out just one of them, literally just a single element, the entire electrochemical loop collapses. The corrosion just completely stops. And that single vulnerability is the foundational secret behind absolutely every smart anti-rust coating we use today. Now, you might be wondering, why can't the metal just protect itself once the rusting starts? Like, doesn't the rust form a shell? Well, no. It's because the final product, the rust itself, or hydrated iron oxide, is incredibly porous and structurally weak. It's kind of like a microscopic sponge. It completely fails to block water and oxygen from pushing deeper. So once steel starts rusting, it will relentlessly drill inward until the entire structure just fails. It literally cannot stop itself, which is exactly why we have to engineer a chemical shield to do it for us. To fight this microscopic war, industrial coatings deploy what is basically a four-part chemical arsenal. You've got your binder or resin for the structural backbone, solvents or water to make it actually spreadable, and specific additives to tweak the final performance. But the undisputed heavyweight champion in this fight, the single factor that actually decides if your metal survives or degrades, is the anti-rust pigment. These pigments are specifically engineered to use their unique chemistry to directly intercept that battery cycle we talked about.
And this brilliantly illustrates exactly how they do it. These pigments go to battle in four completely distinct ways. Chemical protection dissolves slowly to release active ions, basically building a protective passivation film right on the metal. Then there's electrochemical protection. This actually sacrifices itself, using highly active zinc powder to absorb the corrosive damage so your structural steel doesn't have to. Physical barrier protection acts as a literal wall, blocking out water. And finally, conversion protection. This is almost like magic from maintenance crews. It reacts chemically with existing rust and turns it into a stable blue complex, which saves us from having to sandblast everything all the way down to bare metal. Let's look a little closer at that physical barrier mechanism, because it uses an incredibly clever structural trick known in the industry as the maze effect. I love this one. Imagine dropping flat, chemically inert flakes into the paint. As it dries, these flakes naturally align parallel to the metal, overlapping each other kind of like microscopic roof shingles. What this does is force water and oxygen to navigate this long, exhausting, winding maze just to reach the metal surface. It simply starves the corrosion reaction from the outside in. Simple, but incredibly effective. Now, for decades, heavy industry relied heavily on what we might call the toxic titans. On one hand, you had legacy lead, specifically red lead. This was proven over a century to form a really tough, gap-filling layer that totally suppresses corrosion. On the other hand, you had legacy chromate, or hexavalent chromium. This was the undisputed gold standard for aerospace, especially when you're dealing with lightweight alloys. But here is the massive conflict that completely redefined modern B2B manufacturing. Their unparalleled engineering performance came with an absolute catastrophic cost to human health and the environment. Because chemically speaking, hexavalent chromium was, well, it was practically magic. If water managed to break through the paint, chromate ions would literally migrate straight to the vulnerable anodic sites on their own, forming an instant, dense protective film. Even wilder, if the paint was scratched, the chromates would flow into the scratch and heal the wound themselves. It's real-life, self-healing tech.
But, and this is a massive critical but, it is highly toxic and severely carcinogenic. So no matter how phenomenally it performed in the field, strict global regulations rightfully forced it out. The industry had a huge problem. They had to pivot, and they had to do it fast. So where does that leave us? Well, that massive pivot brings us to the green revolution in industrial coatings. Driven by strict global compliance, the chemical industry didn't just adapt, it innovated. We are now engineering eco-friendly, non-toxic alternatives that actually rival the performance of those legacy titans. The real stars of this modern movement are phosphates, molybdates, and borates. These are the smart, highly sustainable solutions that are defining the very future of industrial protection. Let's start with a modern workhorse of the group, zinc phosphate. It gives us extremely low toxicity right alongside a brilliant multi-layered defense system. When moisture hits it, it naturally hydrolyzes to balance out the local acidity. It then binds with vulnerable iron ions to physically plug up those microscopic corrosion sites. But it actually goes even further. The zinc cross-links with the paint's resin itself, physically tightening the whole structural coating. It even reacts with existing rust to neutralize it. It's a true all-in-one multi-tool of green chemistry. Now, what's really interesting about this slide is how chemical engineering just keeps iterating and improving. While standard zinc phosphate is great at forming a protective layer, we now have this upgraded premium option, aluminum tripolyphosphate. Thanks to its unique molecular chain, it acts like a much stronger, more versatile chemical claw. It doesn't just bind with standard iron ions. It actively locks onto multiple states of iron simultaneously. The end result? A much denser, far more stable protective film for your most critical assets. Next up, we've got the molybdates. If you are dealing with a brutal, high chloride environment, say an offshore oil rig where salt spray causes really devastating localized pitting, molybdates are absolutely your champions. They aggressively compete directly with the salt for space on the metal, effectively blocking the chloride out entirely. However, there's a really fascinating engineering catch here. They require environmental oxygen to keep that shield up. So if you're designing a coating for, say, deep underwater immersion where oxygen is scarce, their performance is going to drop. You really have to know your environment. Because, every single molecule has its own natural limitations, just like that oxygen requirement we just mentioned. Modern chemical engineering relies heavily on synergy. We combine these smart chemicals so that 1 + 1 actually equals 3. For example, pairing phosphates with molybdates is just a brilliant strategy. The phosphates get to work instantly, building that base physical block. Then, the molybdates layer on top of that to add that vital resistance against salt pitting. They perfectly cover each other's blind spots. And this actually brings us to one of my absolute favorite structural innovations, the core shell structure, specifically using barium metaborate. See, the age-old problem with chemical inhibitors is that if they dissolve too fast, the paint just loses its protection prematurely. The Vicks? Engineers wrapped an active, rust-fighting alkaline core completely inside an inert silicon dioxide shell. The shell basically acts like a microscopic filter, perfectly controlling the slow, steady release of the active ingredients. You get all the immediate power of the chemical, but with a drastically extended lifespan. It's just brilliant design. So here is the ultimate question for today's industrial leaders. We've mapped out exactly how the electrochemical battery of corrosion can be broken. We've seen the absolutely essential shift away from toxic heavy metals, and we've explored the brilliant, self-healing, smart molecules that are replacing them today. As global standards demand better performance with absolutely zero environmental compromise, how will you leverage this cutting-edge green chemistry in your next specification? Thanks so much for exploring this with me on today's Explainer. I'll see you next time as we continue to unpack the incredible science driving our industry forward.